Friends, today we are going to start a new chapter in physics, that is mechanical properties of solid. So till now we have completed many chapters of physics, that is Newton's laws of motion, circular motion. So today we are going to go with another topic, that is the mechanical properties of solid. This is our part number 1, and in today's video we will be discussing about these topics. Today's video is going to be an introductory video wherein we are going to learn about the introduction, that is what is elasticity, what is plasticity, which is a perfectly elastic body, which is a perfectly plastic body. Then we'll be learning about what is stress, what is strain. These are the two types of forces which we'll be learning. Then we have Hooke's law, we'll be discussing about the Hooke's law, and then the last we have the elasticity graph. Usually this graph is taught during the last time, like during the last part of the chapter, but we are going to learn it first because it builds up the basic of this chapter. So let us start. So first one, as the topic says, mechanical properties of solid. We will be reacting or we will be discussing about the topic wherein how solids react to the forces applied on them. When we apply force on a solid, how it changes. What is the force which makes the solid or which makes the solids or the metal or what material, whatever we are taking, what makes it change its property, change its shape, change its volume. So this we'll be discussing in this chapter. And starting with the first topic, it is elasticity and plasticity. So let us start with the topic of elasticity. So first, what is the meaning of the word elasticity? So as the word suggests, elasticity, we think that something which is elastic or anything which can be pushed or pulled or be stretched at any extent, that is known as elastic according to our definition. So what is this? Elasticity. So whenever we think of elasticity, what comes in our mind? A rubber band or anything made out of rubber comes in our mind when we think about elasticity. But what is the actual definition of elasticity? The property of a material to come back to its original configuration after the force is applied or force applied is released. Now what is the meaning of this? So when we talk about elasticity, we think about a rubber, and our assumption, our stereotype is correct because we are correct in defining rubber as an elastic body. But the way we define it, that is different. When we think of our own conventional method, elastic means something which can be pulled or stretched. But in physics, elasticity means the ability of an object to come back to its original place. So when we take a rubber band, when we stretch it and when we leave it, that rubber band comes to its original shape, original size, original configuration. So this is very important because we don't only talk about the shape size, we talk about its configuration, volume, density, whatever it is. So it comes back to its original configuration. That is known as an elastic object, or this property is known as elasticity. Now there is one very important question of this topic, which is more elastic? Okay, let me write down here. So there is one very good and very important question which is asked many times in many exams. The question is, which is more elastic? Option A, rubber, or option B, steel. This is the most famous question which is asked from this chapter, and the answer to this question, as we assume, it might be rubber, but actually it is steel. Now many people get confused that how is steel more elastic than a rubber? Usually when we think about something elastic, rubber comes in our mind. But the most popular example of steel being a more elastic object is given by using a steel scale. So what people explain this is that when you take a rubber, when you stretch it and when you release it, it does come back to its original place, but it takes some time. I think that is known as relaxation time. So that time taken of rubber is short, it's good. But when we take a steel, we take a steel scale. When we take a steel scale and when we press it from one hand and then we release it like this, what happens is a steel comes back to its original place much faster than a rubber. For example, this is a steel scale. When I pull it from here and leave it, it comes back to its original place. But the speed of this coming back to its original place or its original configuration is much faster than that of a rubber. So that is why steel is considered more elastic than rubber. Now, this was one concept. After this, there is one more concept of a perfectly elastic body. Perfectly, or this is usually said as an ideally elastic body or perfect. Perfectly elastic. So whenever we talk about anything being perfect or anything being ideal, that is usually not existent or that is not practical. But there is one very close elastic body, close perfectly elastic body, that is iota. Iota of a heart is very closely resembling to a perfectly elastic body. What is the meaning of perfectly elastic body? A perfectly elastic body is a body which can come back 100% to its original configuration. Now, if you talk about a rubber band, when we keep on stretching it, pulling it, and after some times what happens is this rubber gets expanded. So this does shows elasticity, but this is not perfectly elastic because after few usage, after some time, the elasticity of this rubber decreases. But if you take human iota, what is iota? Iota is an artery. Like the biggest artery or the first vein or the first blood vessel of the body is known as an iota. And iota is thick, it supplies blood from the left ventricle to all the parts of the body. And iota is considered to be a perfectly elastic body. Now, this was the concept of elasticity, the property of a material to come back to its original configuration after force is applied. That after the force applied is released. Yes, this is one very important point. When the force we apply, that is supposed to be released. When you apply a force on a rubber band, this does not show elasticity, because even if you take some metals which are ductile, if you take gold, if you try to pull a gold, it also becomes into wire. In fact, as we have learned in 10th class, that even 2 grams of gold can make up to 2 kilometers of length of a wire. That is called as ductility. So gold has the most ductility. But if it apply force on the gold, it does turn into wire. But can we define elasticity with it? No, because elasticity is the property to come back to its original place. So after expanding the gold, when you release it, if it comes back, then it is said to be elastic. But here it is not elastic in the case of gold. Hence the important point is force applied is released. When we release the force, then when it comes back to its original place, that property is known as elasticity. So this was our first concept about elasticity. The next concept is about plasticity. So let us see what is the meaning of plasticity. Now let us discuss the second topic, that is plasticity. Now this plasticity is also just a property which is opposite to elasticity. Now what is plasticity? As we have taken example of a gold, when we take gold, we stretch it. So it forms wire, it forms thin wires of very long length. This property is called as ductility. Now when you release that gold, it does not come back to its original place. So that property is known as plasticity. So plasticity is a property wherein the material does not come back to its original position. So the property by which a material does not come back to its original position or configuration, right? Is called plasticity. So it is a property by which a material does not come back to its original configuration is called plasticity, but actually it will be original configuration after the force is released. Is called as plasticity. Now if we take an example, as we have taken the example of metals, there are many such examples. Even if you take an example of a glass, so when you take glass that is the material, if you take glass, if you leave the glass, it falls on the floor and shatters. Now, can this shattering be come back to its original place? It is not possible naturally. But the thing is, the material does not come back to its original configuration. So when you drop the glass, it changes its properties. Which properties? Mechanical properties. It changes its property, it changes its configuration, and the big piece, the big volume turns into many smaller volumes. That is one case. And now when we discuss about perfectly plastic body, we don't have as such many good examples. Like, we have many examples actually, not as such good examples. But when we talk about a perfectly plastic body, we have usually examples of mud, clay. So when you take a clay, for example, now you took clay and let us take this marker. So if I take this marker, if I take a handspan of clay and if I put the marker inside the clay, or if I press the marker in the clay and if I take the marker away, that marker shape is embalmed inside. That marker shape is fixed inside. And that shape does not regain until or unless some other force is applied. So hence when we talk about a perfectly plastic body, we usually consider mud or clay. So perfectly plastic body, it is usually taken as mud, clay. Okay, out of mud and clay, even if you leave the mud, if you take clay, that is much better. Because if you take mud, there are some type of mud which are more like slimy. So if you apply force on them, if you release the force, then also some property comes back. And what is the meaning of perfectly? Perfectly plastic means that object does not come back to its original place or original configuration in any method. Like we have taken an example of iota, right? So when we apply force on it, when you release it, it comes back to original place. So there is no deformation. Because when we talk the case about rubber band, if you keep on using it, even after some time, it gets elastic, that's correct. But it does not come back completely to its original place. So its elasticity decreases. Similarly, in plasticity, when an object which is said to be plastic, when it regains its configuration somewhat or the other, then it is not said as perfectly plastic body. Hence, we usually take clay as a perfectly plastic body. So thus we have completed the second concept, that is a property by which a material does not come back to its original position after the force is released. Is called as plasticity. Now moving on to the main part of this video and the main part of the chapter, that is stress and strain. Stress is nothing but a force, and how is this different from other forces? Let us see. So now let us talk about a force that is called as stress. Now what is stress and how is stress different from other types of forces? Before moving to the definition, let us try to understand this with the help of an example. So now let us suppose this is a body, or a much better body will be here. Let us suppose this is a body with a fixed area. What area? Cross-sectional area. So this body is just like a cylinder, somewhat like this. Now suppose we apply force over here. Force. How much force? Let us say 10 newtons, or let us take 50 newtons. 50 newtons. Now, as we have learned from Newton's third law states that every action has equal and opposite reaction. So every action has an equal and opposite reaction. So when we apply a force on this is called as F applied. This is called as applied force. Now whenever you apply a force on the body also applies force back on you. So let us remove this from here. The body will also apply some force on you, and that will be called as FREF. Now this is called as reforming force. Reforming force is nothing but whenever I try, like for example, this is a marker. Now this marker has a shape and I have the power to change the shape of this. When I try to push this marker, it will not budge, it will not move. Why? Because it is also experiencing some force towards me, and that force is called as F reforming, and usually F applied is equals to F reforming. and this is generally usually case when applied force is equal to the reforming force. So what happens is when I apply some force, that too on a unit like a unit area, let's say unit area, then unit area means it has a area of 1 unit. So it can be 1 centimeter square, 1 meter square, 1 unit square. That is the area, that is the unit of the area. So when I apply some force on an object at a certain cross-sectional area, then the object also applies some force back to me, and that force is called as reforming force. So stress is defined as force per unit area or force per area, and this stress is represented by the symbol of sigma. So this means sigma. Sigma is a Greek letter, it is a letter, sorry, it is not Greek, it is a letter which is used to denote the property of stress. Now stress is given as force per area, and this force is generally taken as F reforming per area, that is cross sectional area. Now talking about sigma, stress unit is Newton per meter square. This is the unit of stress. Now actually the thing is, this force per unit area is the formula of pressure also. So can we say stress is equal to pressure? Stress is not directly equal to pressure, but stress is just like a pressure. The thing is, here in pressure we take the applied force, the force which we are applying, and in stress we take the reforming force, the force which the body is applying, which the object is applying on us. That is taken as a stress. Stress is usually experienced, pressure is something which we provide. Stress is something which is experienced by the body. This body is experiencing the stress, and that stress it is providing back to us. So pressure we are applying, that both have the same formula, force per unit area. But pressure is something which we are applying, stress is something the object is applying on us. So this makes them both different, and this is the concept of stress. So stress is said as the reforming force, which is reforming form by the body, which helps it to prevent it from changing the shape, or which helps it to prevent it from being deformed. If there is no reforming force, when I apply force, the object becomes deformed, which means the shape of the object changes. So we are talking about a property, or we are talking about a force which opposes this deformation. That force is called as reformation force. So hence we can take the concept that stress is equals to force which is reformation force per unit area, and that area is usually taken as cross sectional area. What is the meaning of cross sectional area? When we talk about this shape, when we take this cylinder, like this is our cylinder, right? When we take this cylinder, this has some circular part. When we take it like this, we find the circular part. The area of this circle is known as cross sectional area, and we have to use this area along with the reformation force to find out the stress. Now this was the concept of stress. After stress comes the concept of strain. Now strain and stress both are almost like come together. They both are usually found together. The resultant of the stress is strain. Okay. Strain is represented with epsilon. This is also a symbol. Now, what is the meaning of strain? Earlier we have learned one property, that is one force which is known as spring force. Let me just drop this here. So we have learned about spring force. That is equals to minus of k times x. This denotes the relation between force and displacement. What is x? Let me explain this concept. When this is a spring, the spring has some coefficient, or this spring coefficient, that is known as k. So when you take this end of a spring and when you pull it, it produces some displacement. The spring loosens. Now suppose this was the distance x. Now let us not take x. Distance d. Later what happens? This is the distance d. It increases by some distance x. Now this increased distance, this x is proportional to the force applied. How much force we apply, that much displacement occurs. This is one concept of spring force. The same concept is applied over here. Strain. Now before moving on to the explanation, let me tell you the formula of strain. epsilon is equals to delta L by L, which means the ratio of change in configuration of a body is called strain, and this strain is unitless. Why is it unitless? Because this is change. Now when you talk about the change in length, that is also considered in meter. When you talk about length, it is also considered in meter. Meter gets cancelled. Even we see that this is a ratio. So the ratio is always unitless. So this is unitless. And this is the formula for strain. This is the formula for strain. Now let us understand the meaning of this strain with the application. So now coming to the application, let us again take the cylindrical object which we had. This is the same object. Now here we are assuming it has a distance or length as L. This has length L. Now we are applying a force over here F. This force is called deformation force as applied force. Let this force be again 15 newtons. Now when we are pulling this, see, of course there is a pulling force or pushing force, or when we talk about deformation force, then also there is a reformation force. But sometimes when we apply too much force which breaks the point of the reformation force, then the object gets deformed. So suppose this object gets extended. Now this was the distance L. Now this is called as delta L. Now what is delta L? Delta is change in length. The change in length is called as delta L. So now here we took the object, we applied a pulling force this time. After pulling it, we extended the object, and now this object has become delta L. Now what happened is we have spoken about spring force. What was spring force? We took the spring and we pulled it. What happened? The spring was extended. We took the object and we pulled it. The object got extended. Is there a relation between these two? Yes, there is definitely a relation. But here, if you take our spring force, the thing is there is one law which is called as Hooke's law. This Hooke's law provokes the relation between stress and strain. Now, if you talk about the relation between stress and strain, it is nothing but similarly this force, the spring force and this type of strain. These both, how are they both interrelated? This is what it explains. So, E is equal to delta L by L. That similarly it is just like X. Now this X is what? The extension. So when we took an object and we extended it, we found that the object is extended. This extension is shown by strain. Strain shows how much the object has extended its original. So that is why we call it as delta L. Suppose this length was 10 meters and then we extended it by more 5 meters. Then what happens? E is equals to delta L. What is delta L? Then delta L is actually the final, right? So let us suppose we extended it up to 15 meters. So delta L will be 15 minus 10, that is equals to 5. So 5 by, what was the original length? 10. That is equals to 0. Or 1 by 2, 0.5. It means that we have extended the object, we have extended the body by 0.5 times. So when we apply a force of 50 Newton on an object of length 10 meter, when we apply 50 Newton, then what happens is that object increases its length by 0.5 times. So this was the concept of stress and strain. Now let us move on to a very important relation or a very important law which provokes the relation between the stress and strain. Now that law is known as Hooke's law. Now what is Hooke's law? Hooke's law was given by a scientist called Hooke, and he has given a law that is defining the relation between a stress and a strain. This is Hooke's law. Hooke's law states that the stress is directly proportional to strain. So it can state that stress proportional to strain, that is sigma proportional to epsilon. This is what he has stated. Hook. So can we understand this? Of course we can understand this. Stress directly proportional to strain. So what is stress? As said before, stress is nothing but a force, which is a force applied on an object. When we take an object, when we apply force on it, that force is called as stress. Actually the force experienced by the body given to us is called as stress. But that force, both forces are equal. That is called as stress. So how much stress we apply, how much force we apply, that much will the elongation be. Like we are seeing in the case of spring. When we take a spring, when we elongate or when we pull a string, it expands. Now if you apply more force, it expands more. If you apply less force, it expands less. So if we apply more force, so suppose our force is more, then our elongation is also more. Okay, so hence we can say that sigma is proportional to epsilon. But can we understand it in a much better way? Yes, we can. So we know the spring force. Why are we always talking about spring force? Because I want to relate this force with the stress. These both, the concept of strain, stress and spring force are almost equal or almost same. That is why we try to relate them with the concept. So Fst is equals to minus Kx. Let us keep that aside. From here what relation do we get? We get that force is directly proportional to the displacement. How much force we apply, that much the object expands, elongates, the spring elongates. Now we know that sigma is force per unit area. This is proportional to delta L by N. Okay, so it means that from here we can consider that force is directly proportional to delta L. Okay, now what is X? X is nothing but a change in length of spring. What is delta L? Change in length of object. Now if this force is proportional to delta L, this force is proportional to delta X. So can we say Hooke's law, spring force, all are same, just there is a different representation. Here he has proven that the stress is proportional to strain, and here we already know the concept of spring force. So both can be verified. So hence whatever Hooke said is correct. This was the Hooke's law. Now moving on to the final part of this video, that is the elasticity graph. That will show you the behavior of a elastic material when we apply force on it. So let us see. So now we are going to learn about the elastic body behavior by the help of the graph. So from the Hooke's law we understood that the stress is proportional to strain. So if one more concept between that is, when we say that stress is proportional to strain, when we draw a graph between a stress and a strain, then this graph is said to be linear. This graph is a linear graph. It means that how much stress you apply, that much strain you get. So the ratio of them will be equal always. So this was another small concept hidden between. Now the thing is, we know about elastic bodies. Iota is said to be perfectly elastic, but we still are not practical about its usage. So the more practical usage is of a rubber band. So we are going to take an example of a rubber band and we are going to understand how it behaves under the different force situation. Now what we are going to do is we are going to take a rubber band and we are going to try to expand it. Now here we have a graph at y-axis which describes the force applied, and at x-axis we will understand. Now when we keep on applying the force, this was the graph we obtained. Now what is this thing? So it means that this is the difference between the stress and a strain or whatever you want. The thing is, let us take the origin as O and let us take this as a point A. Or not this, let us take it more at a point A. Now what is this? So ignore the curves, but this is actually a linear. It means that till A there is a force which is applied. Okay. Now what is that force? What does this graph represent? It represents that when you take an object, when you apply force, you apply a force, when you leave it, it comes back to its original place. When you apply it more, it comes back to its original place. When you apply it too much, leave it, it still comes back to its original place. This is the limit. So it means that this is the actual force which you can apply, after which it comes back to its limit. Okay. Now there is still one, it can still go a little bit more. Let me draw it much better. This is said to be as point A. After this, if you apply a bit more force, it reaches a point B, and this point is called as yield point. And this comes to a point C. This is called as lower yield point. Let me write it up. I'll explain everything. After this, it goes like this. This is point D and this is point E, and this is called as ultimate yield point, and E is called as breaking point. Now, what does this represent? One more thing is about C is we have to draw something like this. And this, let us take this as point P. This is called as permanent set. Now, what is this curve? The thing is, now we have to understand this very slowly and very properly. The thing is, when you increase the force from here, we are increasing the force. We are taking a rubber band, we are increasing the force. We pulled it, we left it. We again pulled it a little bit more and then we left it. We pulled it too much and then we left it. Now the thing is, there is some limit of the elastic body, that is rubber. So we can pull it to up to some limit. And what is that limit over here? Point E. After this point, if you put a lot of force on the rubber band, it ultimately breaks. So that point, when the rubber band breaks on applying too much force, that point is called as breaking point. Okay. Now coming to this part of the graph. This part is called as OA part, that is where you are applying a force and you are leaving, it is coming back to its original place. So what we did is, we applied force till here, we applied this much force, when we left it, it came back to its original place. Now it goes till A and then till B also. So B is a maximum point up to which if you leave it, it comes back, but at point B there is some deformation. So actually till point A is till some force limit A. Till the force limit A, when you apply force, when you leave it, the rubber band comes back to its original place without any deformation. But when you apply a little bit more force, then what happens is the rubber band comes back to its original place, but the configuration is not exactly. The rubber band gets a little bit stretched. Okay, so first it was proper till some limit. If you pull the rubber band and when you leave it, it comes back to its original configuration and original shape. After some time, when you use a little bit more force, then the rubber band still comes back to its place, but not originally, because some deformation is noticed, some elasticity is noticed. The rubber band gets a little bit elongated or a little bit elastic. So after this, if you leave it, the rubber still goes to its original place, but the thing is, it gets a little bit deformed. At point C, this is called as this point B is called as yield point. Okay. Now after point C, at point C, what happens is, when you leave the rubber band, it does not go to its original place. Till point B, there is very slight deformation, but up to point C, it does not go back to its original point. If this was the original, if this was the length of the rubber band, up to point C, the length of the rubber band becomes like this. It elongates a lot. So that is called as a lower yield point. Now, after this, it is known as brittle point, or this is known as plastic point. Plastic limit. It means that after C, if you extend it, when you leave it, it will ultimately break, because this is called as a plastic limit, and this plastic limit is used to determine whether an object is capable of making a wires or not. Because after this plastic limit, it will either break or it will remain in that position itself. This can be taken for some other objects other than rubber, because rubber does not remain in that place, it shrinks a little bit. But if you take for example gold, so if you keep on pulling the gold, it will not come back to its original place. So that property is used to define ductility. So this plastic limit. So the thing is, for any elastic material, when you apply force till a certain point A, when you leave it, it comes back to its original place. When you take more force, when you apply more force, force B, then it comes back to the original place, but there's little bit deformation starting to take place. That is called as yield point. From the point where deformation starts, when you apply a lot of force, it will not come back to its original position. It will be too much deformed. At point D onwards, after point C, if you try to leave the object, when you leave the force, when you relax the force, the object does not go back to its original position. It stays as it is. And then point E is called as ultimate point or breaking point, after which if you apply force, the object breaks. So this was the elastic body behavior. So in today's video, we learned about stress, we learned about strain, we learned about elasticity, plasticity, and the graph and Hooke's law. So I hope you enjoyed today's video. In the next video, we'll be learning about Young's modulus, types of stress, types of strain, and even Poisson's ratio. So let us see you in the next video. I hope you enjoyed this video. Do like this video if you enjoyed it. Subscribe to this channel if you're new. See you next time in the next video. Thank you and goodbye.